Hi, in this video, we'll be continuing our study of ODEs, and in the previous video, we just proved the existence and uniqueness of solutions to first order linear equations. So in this chapter, now we'll move on to second order linear equations for ODEs. And what does it mean to be second order? Well, it just means that now it has a d squared y dx squared inside the equation. To be linear, it is the similar formulation where it is linear in terms of the y's, and the t's can be in any form. Then we can say that the equation is homogeneous when the t term just is 0 and non-homogeneous otherwise. We shall now focus just on the homogeneous equations first, as there will be a technique to solving it. So again, there can be initial conditions, and in this time, because so if you think about it, when you integrate a first order, you will have a constant c. So for second order, we need to integrate twice in a sense, which gives us c1 and c2. So in that case, we'll need two initial conditions in order to solve for both constants. Let's take an example on how we're going to solve a second order ODE. So this is a motivating example. So we got the example d squared y dx squared minus dy dx minus y equals to 0. So in this case, we might be thinking, is there any property of a function such that the second derivative equals to the function itself? Then yes, there is, because that is just e to the power of t. So that's one function that works. And if you realize, because when you do when you solve for ODE, what you get is the family of solutions. So you need to ensure that all the solutions are inside. And we actually realize that another function works. So in this case now, two functions satisfy this equation instead of the usual unique function that satisfy the solution in first order case. And with further experimentation, we can see that constant multiples of these two solutions will also be a solution. For example, 2et and 5e minus t also satisfy this. And hence, we can say that c1y1 is a solution and c2y2 is also a solution. And another important thing to note is that the sum of any of these solutions is also a solution. And this means we can say that a linear combination of these solutions is a solution to the ODE. And we can indeed verify this by checking the following formula. Thus, we see that we just need to find two functions that work, and it follows that the general linear combination will work as well. So this is what we notice, and we'll later state it in clearer terms. So now that we know what is a solution that works and no other solution will work, we want to express the infinite number of solutions of the ODE. But we are given some initial conditions, so we need to solve for them. And we just say that y0 is 2, so c1 plus c2 is 2, and then we differentiate to get y prime 0, and it is minus 1, and we solve for c1 and c2, and in the end we just get a solution to the IVP. So I hope you can see how we solve this. So this allows us to solve for the solution. So you might be thinking, how would I ever know there is e to the power or something? And what's good is that if it is a homogeneous equation, if we look at the general case, we actually can say that the solutions will be exponential. So it exploits the two ideas by solving the coefficients and satisfying any initial conditions. We start by seeking an exponential solution of the form y equals to e to the power t. It then follows that y prime is this and y double prime is this. And we substitute into here, we can actually pull out the e to the power rt, and it actually says, and if this equals to 0, it means that this portion over here, the coefficient ar squared plus br plus c, must equal to 0. And this equation is known as the characteristic equation to the ODE. And because its significance lies in the fact that if r is a root to the polynomial, then y equals to rt is a solution. And because it will be a quadratic equation, therefore there will be two solutions only. And so we first consider there will be three cases when you solve a quadratic. So you either are real and distinct, or you're real and the same, or you're just complex conjugates of one another. And this means that the general form of the ODE, if we just look at the first case first, so we assume that they are real and distinct, the general form will be of the following this. So it's C1 e r1t plus C2 e to the power r2t. So this will be how we solve a second order linear equation, homogeneous linear differential equation. And now, so let's just take a look at how we use this technique into solving second order linear homogeneous differential equations. So first we need to find the general solution of this ODE. So what does it? We first assume that y equals to rt, and we say that r must be a root of the characteristic equation, which is r squared plus 5r plus 6 equals to 0. This allows us to find that r1 is minus 2 and r2 is minus 3. With that, this tells us that the general solution is c1 e to the power minus 2t plus c2 e to the power minus 3t. So this is a very quick technique in solving the second order ODE. And then if we were to given initial conditions 2 and 3 respectively, we are able to solve that c1 plus c2 is 2 and minus 2c1 minus 3c2 is 3. This allows us to find that c1 is 9 and c2 is minus 7. This gives us the expression that y equals to 9e minus 2t minus 7e to the power minus 3t to the IVP. And the graph of the solution is shown below. Hence, this is the technique of solving a second order linear ODE, where the roots are real and distinct. So you can look into the textbook to practice. And that's all for this video. Hope you've enjoyed it. Please like, share and subscribe, and I'll catch you in the next one. Bye.